Okay, hi everyone. In this video, I just want to start sort of like blasting through a bunch of derivatives just to remind you of all the rules and stuff. I might break this up into multiple videos if it takes longer than I think, but one thing I would recommend is that you pause the video sort of before I do each one and see if you can figure it out on your own, or once you get the hang of a section, maybe try to figure out some of them on your own. Be better for you than just sort of like passively watching me power through some of these. But let's just do it. Okay, so I'm going to start with number one. So like I said, think about it, pause, but then I'll dive right in. All right, so the thing to remember here is that linear functions, the derivative is constant, right? So this just becomes 17, and constants go away. So this is 17 plus 0, really, for the constant. So that's the 17x becomes 17, the 11 becomes 0. Okay. All right, 2. Well, this is the power rule, right? X squared becomes 2x. So this is 5 times 2x, which is 10x. So remember the power rule, you bring the power down in front. Well, let's look at the next one. You can see this. So like, in fact, maybe I should just put d over dx so I don't have to copy the whole thing. The derivative of that, so remember the idea is you take the 11, you put it down in front, and it becomes 11, and then you subtract 1. So derivative of x to the 11th is 11x to the 10th. And then x to the 8th is minus 8x to the 7th. X to the 4th is plus 4x cubed. And then the constant term disappears. Also that when you differentiate a sum of different things, that it's really just the sum of the derivatives. So these just become, yeah. Okay, how about when it's 3.5? Well, it's the same thing. The 3.5 comes down in front, and then you subtract 1. 3.5 minus 1 is 2.5. All right. One thing to remember when you look at square root of w is remember that is a power, right? That's actually w to the 1/2 power. There's good reasons for that I'm happy to talk about with anyone. But for some reason the square is considered the 1/2 power. And so the derivative of that, now I'm going to differentiate with respect to w. So I'll put a w right there. 1/2. Well, that's 1/2 w. When you subtract 1 from 1/2, you get negative 1/2. And the other thing to think about, so negative powers means 1 over, right? So it's 1/2 times 1 over w to the 1/2. And that's really 1, it's really 1 over 2 root w. It depends on the context. Sometimes this solution's preferable. Sometimes this is fine. The minus 1/2 power is fine sometimes. Okay, let's keep going. So you're getting the hang of it probably. So the derivative of this, same thing. It's 5/4 x to the 1/4, I think, when you subtract 1 from 5/4. Okay, what about 1 over t? Well, 1 over t is t to the minus 1 power. Again, there's good reasons why it's considered the minus 1 power. And so we get minus 1 times t to the minus 2. And t to the minus 2 is 1 over t squared. So you can think of that as minus 1 over t squared. So the derivative of 1 over t is minus 1 over t squared. 1 over x to the 5th. Well, I'll even just go ahead and say that's x to the minus 5. But again, we subtract 1. So this actually becomes minus 5x to the minus 6, right? Because we're subtracting 1 from minus 5. And again, you could rewrite that as minus 5 over x to the 6th. Yeah, I mean, these are kind of all the same. Just trying to blitz you with a bunch of them. You could write that as minus 10 over u to the 11th. I suppose I'll go ahead and do that. If we differentiate with respect to w, Well, okay, it's minus 11/3. And then really the issue is just what happens to when you subtract 1. Minus 11/3 is minus another 3/3. I think it's minus 14/3. Okay. And x cube root of x is x to the 1/3 power. So derivative of x to the 1/3 is 1/3 times x to the negative 2/3. When you subtract 1 from 1/3, you get negative 2/3, which you could rewrite if you really wanted to as 1/3 times the cube root of x squared. The minus sign puts everything in the bottom. The 2 is it's an x squared. The over 3 is a cube root. So you could write it that way. Again, if it actually comes up, I mean, this is mostly fine. It's just if you ever actually want to compute anything, you might have to look at it that way. And then the last one is just the fully general power rule. So it's alpha x to the alpha minus 1. Okay, that's the power rule. Should I just keep going? Maybe I'll keep going instead of making another video. So, okay, let's go to trig functions. Again, please be pausing, trying to see if you can remember stuff. These, you can look at these graphically. There's good reasons. I mean, it really is. The derivative of sine is cosine, if you remember. But the derivative of cosine is minus sine, the negative sine function. So that's the thing to kind of remember. You can, again, look at the graph and see where it's going up and going down. It oscillates. The graph oscillates with period 2 pi. So the slopes on the graph oscillate with period 2 pi. And then you can sort of convince yourself that the slopes match when the derivative of sine, there's actually cosine and stuff. This one, this you probably just remember, or you might remember that tan x is sine x over cosine x, and that there's something called the quotient rule. And so you could rederive this using the quotient rule, but it's 1 over cosine squared x, or what's also known as secant squared of x. Okay. The derivative of sine of a multiple. Thing you're going to do here, this is where first kind of an example of what's called the chain rule, where you have 2 layers here. You have the sine layer, and then you have the times 5 layer. Because you take t, you multiply it by 5, and then you apply the sine function. And when you differentiate, you have to differentiate both layers. So the sine, when you differentiate it, becomes cosine of 5t. Because it's sine of blah, becomes cosine of blah. But then you have to multiply by the derivative of the 5t, right? And the derivative of 5t is just 5. So this is 5 cosine 5t. Okay. You put the 5 in front. It's sort of nice to put the 5 in front. So like these kind of things, you just pop out on multiple. Like if the variable inside is multiplied by a constant and you differentiate, that constant just gets popped out in front. It stays inside also, but a copy of it gets popped out in front. All right, e to the x. You should know this. This is the very special function whose derivative is itself. Derivative of e to the x is e to the x. All right, so then if we go to this one, number 18, the derivative of e to the 5w. Well, it's kind of the same as that previous one, the sine of 5t. It's the derivative of e to the blah. So that's e to the blah times the derivative of the 5w, which is just 5. So similarly to the sine, this pops out a 5 in front. In the earlier case of the sine changed to cosine because the derivative of sine is cosine. Here the e didn't change because e to the derivative of e to the x is e to the x. This is e to the minus 1/3 x, so it's the same thing as the previous one. It pops out a minus 1/3 in front, but it still has the minus x over 3 in the exponent. 2 to the u. There's a rule here, and I can give a little bit of explanation of the rule, but it turns out that it just pops out an ln of 2 times 2 to the u. Natural log of 2 times 2 to the u. Note, the answer is not, u times 2 to the u minus 1. This is not the answer. Okay, it's not the power rule because the variable is in the exponent. Power rule only works when you have the variable in the base and then you have a constant exponent. Here, the constant is in the base and the variable is in the exponent. And it turns out that, so it's an exponential type function, and it turns out that it's this ln of 2 times 2 to the u. Again, maybe I'll give a little bit of a sense why that is. One thing you can do is, let me just write over here on the top right. E and natural log cancel each other out. So if you have something like e to the ln of 2, that equals 2. And so let me just make some room here. So 2 to the u could actually be thought of as e to the ln of 2 to the u, which this is a successive exponent thing. I take e, I raise it to the ln of 2 power, and then I raise it to the u power, and you actually just get the product ln of 2 times u. And so the derivative of this is just like the previous two problems. We're going to pop out an ln of 2 in front. But this thing right here is just this thing right here, which equals 2 to the u. So I can rewrite that. I can replace that with 2 to the u. So that's why that's the only thing that changes. Natural log of 2. Natural log of 2 is about 0.7. Again, we can talk about what that means in a separate video or in class or something. But so that's the idea. That's where that comes from. So similarly here, 21. This is just going to pop out a natural log of 1.01 times 1.01 to the y. Okay. Ln of 1.01 is close to 0, but it's not exactly 0. And then finally, the derivative of ln of x is another famous one, which is kind of remarkable that it doesn't have any logarithms or exponents or anything in it. It just has one. It's just, the derivative is just 1 over x. All right. Maybe I'll do these last ones in a separate video just because it feels like you might want to take a breather for a minute. So I'll stop there and do a part 2.